to our QIQT 2022 forum. Suranjana is an active worker in the area of quantum metrology and quantum sensing, then non-classical states of light, and particularly sub-Planck structure, function, phase-space distribution. Her thesis was primarily the area where wavelet also was used. So Dr. Ghosh is right now associated with us in our QIQT project, sorry, in our DRDO project on quantum sensing. In particular, she has done very recent work which has been communicated to New Journal of Physics using special non-classical states of light to probe basically quantum sensing and quantum metrology, which is going to talk about that precision metrology. But more importantly, these states also can be realized in molecular physics. So as you know, chemistry is using quantum computation, quantum metrology, those kind of things in a very active manner. For example, we physics people are interested in theory, application, those kind of things. Experimental people are taking up quantum communication. But if you really ask me, if you look at use of quantum computation, you see huge like chemistry people. Excited state spectrum, precision, finding of levels, and many phenomena. Drug discovery, drug design, big molecule, many things. So today's Suranjana is known to be a very good speaker. So today she will tell you non-classical states of light and quantum sensing and many more applications. This stage is yours. So 1 hour talk. Take it leisurely, no problem.
Okay. Thank you very much, sir, for your kind introduction. And it's my privilege to be part of this summer school. And I feel also honored to when I get introduced by you, because I have learned many things from you, starting from my PhD days, and still today we have been working together. So it's a quite long journey. We have been working together, and of course, very wonderful experience to work with you. So I want to thank once again for inviting me to deliver my talk here. Okay, so let me share my slides first. Is it visible from other side?
Yes. Yes, you can make it full screen.
Yeah. Okay.
Perfect.
Okay, fine. Okay, so today I'll be talking about quantum interference structures and quantum sensing. So the flow of my talk is follows. First, I will give brief introduction. Why we need to study this field, quantum sensing, why it is so important to develop our future technology. And then what does it mean by this quantum metrology or quantum sensing? And then, of course, what are these quantum interference structures? What is the connection between this field, quantum sensing, and when, especially when the dimension goes below Planck scale, what will be its physical significance? Next, I'll describe the revival and fraction revival phenomena, which basically occurs when we see a long time evolution of a wave packet. And it's very important because I'm going to use those phenomena to get these quantum interference structures whose dimension will go below the Planck scale. So I will briefly explain those phenomena. And then, of course, this quantum superposition or Schrödinger cat states. It's very well-known state, and there is a lot of experiments are going on. And here, actually, in my first approach, I'll discuss some of the results which we got based on the diatomic molecular system, and where first we have considered the vibrational motion, and then we will use also rotational degrees of freedom to see whether we can enhance the sensitivity limit or not. And further also we'll use coherent control method to enhance the sensitivity. And then after that we'll move to another potential, which is postular potential. It has many applications also. You can model different kind of physical situation using this potential. And then finally I'll discuss about this new kind of state, which is twin Schrodinger cat states. It's different from the earlier one, which is Schrodinger cat state. Everyone knows about that. But here, actually, this is our very recent work. We got some interesting result where I will talk about the twin Schrodinger cat states and also its application towards the quantum sensing. And finally, I'll conclude. Okay, so now quantum technology, we know that a lot of works has been going on over this world to develop this new technology, which will be our future technology. And already the first quantum revolution, it happened long before. I think it's around 1950, around that time, when we started using semiconductors, lasers. So that basically, because of that, now we have been using these computers or internet. So that quantum properties we have been using. But thing is, here the information processing is classical information processing. So these are all based on the bits 0 and 1. Now, we need things faster and faster. We need solution of most of the problems very quickly, instantaneously. And that is what actually now we are entering into the world of quantum. And there it shows some different kind of properties that we know, that is quantum superposition or quantum entanglement. So we are going to exploit those properties, and that basically brings our second quantum revolution. So this is basically the reality is that the global race is on. Already we are in the middle of second quantum revolution, because there are certain things already we have been using, for example, the GPS system. But we are looking for, for big change in our society where we can use, this quantum technology. Okay, so this is basically Moore's law. It was predicted by co-founder of Intel long back, 1965, by Gordon Moore. He predicted that the number of transistors, in our computer, we have been using some processors, and there are many number of transistors. Okay, and around that time, he predicted that the number of transistors will be double every 2 years or after 18 months. And it has been followed, actually. You can see this graph. It shows the number of transistors are increasing with the years. And he predicted that around 2020, around that time, this number will be very large, and the dimension will reach to the atomic level. So we cannot go beyond that. And that, because of that reason, actually, we need to develop our new technology, which is a quantum technology, because we are entering into the dimension of atoms, where these microscopic particles behaves completely different way, where we need to consider the properties like quantum superposition or entanglement. So, many industries are working hard to find a solution, and of course, there are a lot of experiments or a lot of work has been going on in this direction to develop the new technology. So that is basically the quantum technology. But there are several domains also to develop this technology. One is quantum computing, quantum cryptography, quantum communication, and of course, this quantum sensing or metrology. But these are all well connected with the field, which is the foundation of quantum mechanics. So it's very important to know this field first, quantum mechanics, and then you can have some specialized knowledge, depending on your interest, and then you can find, some application towards the quantum technology. So here, basically, I'll discuss about this domain, this field. This is quantum sensing or quantum metrology. Okay, so this is basically, it can give you an idea that, worldwide, it's a big amount of money already, got invested to develop this new technology. That is around $30 billion, which is a quite huge amount of money. So different countries, they have been using their, money. And for example, US, they have used a lot of money in that direction. Canada, you can see, this is also one of the world's leading nation in quantum research. They have also invested $1 billion money in that direction. UK also, you can find that they have shown increasing participation, in quantum research, and they have very strong collaboration between industry and academia. China, of course, it has already established itself as a leader in quantum communication. and they have already made a record for solving a complex problem, because in 2019 Google reported that they have developed a qubit, they developed a processor with 53 qubits, and they have solved a problem which took time almost 3 minutes. But using this, our classical super fast computer, even if you can use, that will take 2.5 days time. But in the last year, I think in 2021, October, around that time, China, they use a processor which is having 66 qubits, and they reported that the same kind of work they have done, which is quite faster, 1 million times faster, they can solve the same problem. So we can see that a lot of progress is happening throughout this world, and very recently also Indian government also, they spent a lot of money to develop this technology, which is approximately $1 billion. So we can see we are not very far from our new technology. Okay, now what is the quantum sensors? So quantum sensor basically utilizes quantum states for measurement. So, but there is a very challenging part, because these quantum states are very sensitive. So if you want to use these quantum state for measurement of any kind of quantum parameters, then we have to first isolate those quantum states. That is the main challenge actually. If we can isolate, then we can make use of those quantum states to develop new kind of techniques to measure these quantum parameters. So that is the main challenge. If we can overcome that challenge, then we can develop new quantum sensors, and that can change our life. What already available? See, atomic clock, it is already available, and these are today commercially available in fingernail size. And there are many actually atomic clock. Then researchers are now turning to atomic transitions at optical or even ultraviolet frequencies. So many more actually are available. So already a lot of development it happened, but in future also we are expecting some more. For example, if you want to know what is exactly happening under the Earth's surface, or if you want to focus the volcano eruption or earthquake, or if you can predict very precisely weather, so that these are it's going to change our life completely. Also in the medical domain, there are a lot of application. Currently, the MRI scanner basically generates 3D model of a brain, and doctors basically use to treat our neurological diseases. But these are very expensive, large, and noisy. But quantum imaging can will make it very small and portable also, and there will be some advantages over there. Now, early diagnosis of disease, that's very important part, because already we are going through this pandemic situation. So if we can detect or diagnose the disease and can have the medicine, we can save many human lives. So of course it will bring miracle in human life. Now, present navigation system, it basically rely on GPS, which depends on a radio receiver, and that is quite easy to jam or mislead. But if you use quantum navigation system, these are very hard to fake, because they are based on fundamental properties of nature. And military or defense sector, there are a lot of application in that domain. It could provide alternate positioning or navigation. If you can use these quantum sensors, it could lead to significant improvement in submarine detection. It can play important role in intelligence or surveillance. So there are a lot of application. I've just given few examples here, and can see that how fast this field is developing from very basic science to very useful applications. Okay, so this already I mentioned about this field. Basically, quantum metrology field, it deals with that how precisely one can measure quantum parameters. So this field promises to develop measurement techniques that give better precision than the same measurement performed in a classical framework. So using the classical protocols, we can reach to our ultimate limit, but to beat that limit, we have to use these quantum properties. That is exactly the field quantum metrology deals with that. Now, question is how precisely one can measure the quantum parameters. See, if we measure any parameter, if we do any kind of measurement, there will be some statistical error. And to minimize that kind of errors, we can repeat that measurement procedure, for example, in number of times, and that basically reduces the error, and it scales as 1/√10. That is the standard quantum limit. And this is the ultimate limit one can reach using the classical protocols. Now, question is, can you beat this limit? Answer is yes. If you use these quantum properties, for example, this quantum superposition, quantum entanglement, then we can enhance this sensitivity √10 times and can reach to this Heisenberg limit, which is order 1/n. Okay, so now question is, what is the connection between this smallest quantum interference structure with this field? So that basically this quantum metrology field means we are dealing with the measurement process of, it can be anything. It can be electric field, magnetic field, or any kind of weak forces we can measure. Gravitational wave detection is one of the, example that the Einstein predicted 100 years ago, but now today experimentally we got the evidence of that because of the very advanced level instrument using the interferometer. So that is only possible because of this advancement. So that's using this field we can measure many things. This kind of small, very weak forces that can cause kind of small displacement or small rotation of quantum states. And this basically it will be very, very well connected if we have very small interference region which is present in a quantum state that will detect fast that there is some kind of disturbance, or any kind of coupling with the environment. So they are very, very sensitive to detect any kind of external perturbation. So that basically first pointed out by Professor Zurek in a paper, Nature paper 2001, and he mentioned about the sub-Planck scale structure. So this dimension is very small. It can be below the Planck scale. So automatically we have an idea that whether is it violating the Heisenberg's uncertainty principle or not. No, it's not violating the uncertainty principle. Basically, it gives a total effective phase space support. But the smallest region, which we are calling the sub-Planck scale structure, is a part of this total system. So that basically physically significant. So what are sub-Planck scale structures? So because of this Heisenberg's uncertainty principle, automatically it gives an idea that there should not be anything which can go below this Planck scale, or even if they exist, they do not matter. But that common assumption is false. So these sub-Planck scale structures are physically significant, and it plays a very important role. If there is any kind of perturbation or disturbance, then these structures will detect fast. So if an act of measurement or any other process, it perturbs the system by a very small amount in phase space, the sub-Planck structure will allow the resultant state to be distinguishable from the old one. So even this disturbance is very small, it can cause a very small displacement or rotation of the quantum state. That these two states, one which is the older one and another one which is after the perturbation, these two becomes quasi orthogonal. So we can distinguish these two states and can make use of can find the measuring this small displacement, one can connect with the source where from the disturbance came and can measure the weak signal. So of course these structures, it plays very crucial role in Heisenberg limited measurement. Okay, so now this is, I'll explain about this phenomena, which is the revival and fraction revival phenomena. Let me start with the basic thing that, quantum mechanically, we deal with the wave functions, and the measurable quantity is, chi mod square. And the wave packet, when we define a particle, we define the particle using the wave packet. It's kind of superposition of quantum states. So here, chi 0 is an initial wave packet, where n number of states are contributing to form this wave packet, and Cn is the weighting factor. Now, if you see the time evolution of that wave packet, so this is Psi RT, the time dependent wave packet, and there you can see right hand side is the phase part. So depending on the energy, how it depends on the quantum number n, we can see some interesting phenomena. Okay, so revival. What is revival? If a system, it evolves with time and then comes back to its initial state at some time, then we'll say that the system has undergone revival. So, it's very similar, like, our Earth, it is evolving around the sun. So they are just coming back to its own or initial position. So it's reviving after their classical time periods. Okay. Quantum mechanically, similar thing. If we deal with the system which is having the linear dependence, for example, oscillator system. So energy is some constant alpha n. It is dependent linearly. Then at time t equal to 2 pi by alpha, the phase term becomes 1, and it comes back to its initial state. So we say that wave packet is reviving at this time. Now, if it has also quadratic dependence, for example, when it has the energy, okay, one expression I should have written here. Suppose energy is alpha n plus beta n square. So extra quadratic term, if it is there, then because of that quadratic term, it will have some excess phase, and around time t is equal to 2 pi by beta, the excess phase caused by this term will be multiples of 2 pi, and system will again behave like classical. This new time scale is called the revival time. So there are two time scales I've defined. One is the classical TCL, another is T revival, which is coming from the quadratic dependence. But question is, all quantum systems, they're not having this kind of energy, quantum number dependence. So in that case, it is also possible to see this revival phenomena or fraction revival phenomena if we expand the energy in a Taylor series with some condition that n bar should be very high compared to the delta n. Then again, we can see that there are terms, linear and quadratic terms. And from there, again, one can write the time scales, can have the expression of wave packet in terms of this TCL and T revival. Okay, so this is fractional revival. So already I have explained about this revival phenomena. Now this fraction revival, basically it occurs when, at time t equal to 0, when wave packet, starts its evolution and then regains its original state at t revival time. But at in between of these two, there are certain times when t will be rational fraction of t revival time. For example, when it is half of t revival time, or 1/3, or 1/8, 2/3. So all this time, the initial wave packet, it splits into mini wave packets, and this is called the fraction revival. So it's very interesting to see that the initial wave packet, it splits into several number of subsidiary wave packets, and mathematically one can also check it. Because this quadratic term, this nonlinear phase, can be written as a summation of linear phase using discrete Fourier transform. And here are some conditions actually we need to satisfy. And using that, finally, we can write this wave packet in this form. And see, this is a nice movie I have taken for Riemann atomic wave packet from Straub's web page. Basically, initially, the wave packet is well localized. Now, after reviving after their classical few cycles, it dephasing starts, and then it's going to break into mini wave packets. That is actually the revival phenomena, fraction revival phenomena. So this one can ask why it is breaking into mini parts. So for example, suppose we are considering at 1/3 of t revival time. So r is equal to 1, s is equal to 3. Now you see here this condition that when when s is equal to 3, l is equal to 3. So the summation here, it goes from t is equal to 0 to l minus 1. So 3 minus 1 means 2. So there will be how many terms? 0, 1, and 2. So there will be 3 wave packets, A0, A1, and A2. A basically gives the amplitude. So this way one can check, at what time it will break into how many parts. So they are here. this is this movie is showing that with time, this dephasing starts, and then at some different fraction level time, it's breaking into mini wave packets. And finally, the well-known Schrödinger cat state also found using this fraction revival phenomena when time would be 1/4 of T revival time. So 1/4 of T revival time, S is 4, and using that condition, one can check that there will be two wave packets, A0 and A1. So that two-way breakup is very similar to the Schrödinger cat state. So here actually you can see this is a three-way breakup. It is split it into three parts. Now if we wait for a bit, we'll see that it's again coming to this two-way breakup, right? So it's very similar to this, this Schrödinger cat state. You can see this is a picture I've taken from one of our work. It is in the phase, and these are the two coherent states. And in between, there are some oscillatory, region, that is the quantum interference region. So it's very similar to like the Schrödinger cat state. So we know all about this Schrödinger cat state, but that completely, this behavior we can see in quantum domain. In our classical world, it's very difficult to accept this phenomena, because if I say that I'm holding a pen here in my left hand, and also it is also exists somewhere there at the same time simultaneously, so we cannot accept that statement, right? So that basically this behavior is a kind of audit behavior we can see in the quantum domain. So around that time, Schrödinger he give an example or thought experiment kind of thing to analyze this principle, that he put a cat inside a box, and we kept some radioactive substance there. And the mechanism is like that if the radioactive substance will decay, then it will hit a hammer. That hammer will fall on a bowl which is made of glass, and that bowl basically contains some poison. So that poison will come out, and that will kill the cat. So if we don't open the box, because it will be closed from outside, cat is inside, and all the mechanisms are there. So we don't know when the radioactive substance will decay. So if it is closed from outside, then the question is whether the cat is dead or alive. We cannot say, right? If we open, then only we can find it in a particular state. Either it's dead or alive. But otherwise, we don't know that radioactive substance decays or not. So it's kind of in a superposition state. So it's a kind of thought experiment he did around that time to analyze this. Okay. Okay, so now this is, let me show some results based on some physical system. So here actually I'm starting with a molecular system, diatomic molecular system. And here we are considering the vibrational motions. And here you can see this is the Morse potential, and D is the dissociation energy, beta is the potential parameter, and X is the distance from its equilibrium position. So two atoms are vibrating around this equilibrium position in a diatomic molecule, and these are the corresponding wave functions, and all these parameter values are interconnected, where N is a vibrational quantum number. Okay, so here actually we have considered the bound states only. So dynamical symmetry group is SU2, and these are the corresponding generators. And using that, one can construct the coherent state. Okay, so this is basically introduced by Schrödinger again to describe the non-spreading wave packet for harmonic oscillators. So this coherent state is the most classical object in quantum domain, and it has some interesting features also. So here we have constructed the coherent state using the vibrational levels of a diatomic molecule. So here this chi is the coherent state, and D is the weighting factor. It decides which other level will contribute. Psi, these are the eigenfunctions of the Morse system, and of course this is the phase term where energy looks like this. And again, one can find the time scales, which is the TCL and T revival, which will come in terms of the these potential parameters. Now we have this these time scales. Now we can see the system dynamics, because this coherent state is nothing but a wave packet. So here alpha is the coherence parameter, So we have a freedom, actually, depending on the laser frequency, we can change what are the level will contribute. So when alpha is equal to 0.2, we can see the higher levels are contributing for of the Morse potential. And when alpha is equal to alpha 1.4, lower levels are contributing. When alpha is equal to 2.5, very bottom levels are contributing. And the corresponding initial wave packets, is the probability density in coordinate space. It looks like that. But the first one, it shows is not a very well localized wave packet because of the potential effect is there. But for the other two cases, it's a quite well localized wave packet. And to see the system dynamics, this fraction dynamic phenomena, we need a well localized wave packet. So we have done our study with these two cases. And here you can see the fraction revivals, which these are some snapshots. And initial one, it is basically for t is equal to time when 0 initial wave packet. Now here 1/4 of t revival time. Basically times are scaled by revival time. So 1/4 time of t revival is a kind of fraction revival. So around that time it should break into 2 wave packets. That is what actually happened here. But because of the potential is asymmetric, so these 2 wave packets, it doesn't look similar. Okay, so now at 1/8 of t revival time, you can see the right side, that figure below 1, where it's not clear exactly what is happening. It should split into 4 wave packets, but it's not clear exactly in coordinate space. So because of that reason, we move to phase space, and we have studied the Wigner distribution, which is a very useful tool for visualizing the quantum interference phenomena. So we have calculated this Wigner function, and here you see at 1/8 of t revival time, this basically, to analyze this state, we have divided into different parts, even part, odd part, and the interference part. So figure A basically shows the even part of this state, and that looks very similar to cat states. You can see there are 2 wave packets, and in between some ripples are there, which are basically quantum interference region. So this black and red, these are the positive and negative regions. Similarly for B, this is also the odd part, okay, and it is again a cat-like state, but it's rotated in phase space. And C is showing the quantum interference region. And as a whole, we can see this figure D is showing what is happening here. It's basically split into 4 wave packets, and in between there are some quantum interference ripples are there. Similarly, for the second case, for alpha is equal to 2.5, also the levels are, it's very bottom levels are contributing. So wave packets are very closely spaced. So you can hear the same kind of analysis can be done. And finally, in figure D, we can see the interference structure. It is present at the middle, which is a spotty kind of structures. So we have found this smallest quantum interference region for diatomic molecular system, and also analyze its dimension, because all this study we have done in atomic unit. So we check the dimension, and dimension, the sub-Planck dimension is h bar squared by capital A, which is the classical action. So for these 2 cases, we got the values below 1, which is less than the sub-Planck dimension. So okay, this is a kind of symmetric diagram. It will help students to understand that how these quantum interference structures, it gives some kind of spotty or checkerboard kind of structure. Because for the optical system, when there are 4 coordinate states, okay, it's known as a compass state. It is situated at north, south, east, and west. And at the middle, we can have some kind of checkerboard pattern. You can see here how it is happening. So here we are interested at the middle portion only here. So quantum interference ripples will be parallel to the line joining between them. And here also you can see these are the in quantum interference ripples. When they overlap to each other, we'll get some kind of checkerboard pattern. So this is basically quite obvious when you deal with the symmetric system, but the molecular system is a asymmetric one. So initial wave packets are not very well localized. So these are the individual states, individual wave packets, and when you see the quantum interference region, you can see this kind of structure there. But this, of course, these are the smallest region. The dimension is below Planck scale. So this work actually it was done when I was doing PhD in PRL. and it was initiated by Professor Panigrahi, and we actually first time did it for the diatomic molecular system and got this result. Now question is, are they really sensitive in presence of internal or external perturbation? Okay, so we have shown that we can have this kind of structures in other physical systems also. And here we deal with some other kind of potential, which is a posterior potential. And these are the parameters, kappa and rho. And changing that parameter, we have some freedom here. We can make it symmetric or asymmetric one. So the red line is showing the symmetric one. Black line is showing when there is a very small asymmetricity. And blue line is showing where there is a large asymmetricity. And the corresponding energy and wave functions are there. And using the coherent state, also we have see the system dynamics for this particular type of potential. It's a symmetric kind of analysis we have done. And here you can see very clearly that 1/4 of t revival time, we have just plotted the Wigner distribution function at different fraction revival time. So the first figure is showing the cat state, Schrödinger cat-like states. And the second one is showing the compass like state, north, south, east, and west. And in between, you can have this, smallest quantum interference regions. And at 1/12 of t revival time, it will split into 6 wave packets. So we named it as a bending-like state. So there are 6 states, and also in between one can have some quantum interference regions. So this basically done with the symmetric case. For the asymmetric case also, same kind of analysis can be done. And we have also find this dimension and check the this law that what will be the dimension, is it valid for our other physical system or not. So basically Zurek pointed out for the oscillator system, but we have also shown for other physical system also this law valid, and we also showed in this study. Now question is, if there is any small change or perturbation, can we use or can this sub-Planck structure detect this small perturbation? So there are 2 ways of verifying this thing. One is if there is an internal perturbation that will change the potential very slightly, or the second one is if there is any kind of external perturbation, any weak force, it will make a change as a whole. So maybe it can displace the state, and that basically can be captured at the sub-Planck level. Then we can also detect the weak force. So first one we have studied here. So here you can see the figures, the left side figures. These 2 looks very similar. We cannot distinguish these 2 states as a whole. So this is basically at 1/8 of t revival time, where it looks like a compass state. Now you see the enlarged version of the central region. So this basically, you see the potential here. Very small change occurred. And when you see the total state, we cannot distinguish. But at the level of sub-Planck dimension, you can see there is a small shift. One tile has shifted there. The positive tiles, for this small change of this potential, one positive tiles it's shifted towards the one negative negative tiles. So that's it's very interesting to see that such a small change or displacement can cause these 2 states quasi-orthogonal. So that is what actually overlap function we have calculated, and we show that for a small displacement also these 2 states becomes quasi-orthogonal, and one can distinguish these 2 states. So same thing, we have also checked for the external perturbation and also calculate the displaced coherent state. And here you can see this overlap function we have plotted here, and the single oscillation is the order of it's a very small. Actually, you can see here it's a 0.079 atomic unit, and a single tile, it has dimension of order of 0.075 atomic unit. So almost they are same. So such a small displacement can make these 2 states orthogonal, and one can distinguish these 2 states and can make use of these sub-Planck structures to find some other parameters. Okay, now again, I'll come back to the molecular system. Here, this is another approach we have used, which is a coherent control method to see whether we can enhance the sensitivity limit or not. So one group actually in Japan, they have been working experimentally. They have used iodine molecule, and very challenging tasks they have been observed these quantum ripples or quantum interference phenomena, and also they have designed quantum carpet in their lab. So very challenging task they are dealing with the diatomic molecular system. So using their experimental parameters, have done this study here. So basically, idea is a kind of wave packet interferometry. Instead of using one single pulse, here we need to use two pulses, which can excite two wave packets. These two, optical pulses, they have some kind of relative phase. That we can control this to relative phase. We can control the two wave packet or the system dynamics, or we can also control the quantum interference structures. So basically here, this is the state phi theta, which is a combination of two wave packets, phi 1 and phi 2. Phi 1 is where we have excited the even states, and phi 2 is where we have excited the odd states. And this is the state, okay? Now we'll see the time evolution of that. So here, for a particular time, you can see this theta plays a very crucial role. Depending on that theta, it decides actually what will be the contribution of even part or odd part. So already I have explained about this mode system and its energy time scales. So I'm not going into that. And finally, this is the final result. I'm going into this. So here you see, if you change the parameter theta, and here basically there are two time at 1/8 of t revival time and 1/16 of t revival time. The first row, it basically shows the sub-Planck dimension. We have measured the sub-Planck dimension, changing the theta. And when theta is equal to pi/2, we got the maximum sensitivity at 1/8 of t revival time. And that's the corresponding state. You can see here, it looks like a north, southeast, and west kind of state. But for 1/16 of t revival time, when theta is equal to 0, this gives the maximum sensitive states. So it looks like it's a bit rotated in phase space. It's not like a compass state, but it's a rotated one, and that gives the maximum sensitive states. So that can enhance this limit. So that is what actually we got when we use the coherent control method. Next is there any other way to enhance the quantum sensitivity? So that basically we have included the rotational degrees of freedom, and when you consider the rotation also, it's very difficult to handle because it's a 3D model, and then if we move into the phase space, then we have to deal with the 6-dimensional space. So that will be quite complicated. So here actually I've taken a rotating mode system, which quite nicely capture the rotational effect in one dimension. So basically it's modes, and the centrifugal part is also there. So this is the effective potential, and you can see if there is a coupling with the rotational quantum number j, here at a particular time, the system dynamics is changing. This is basically at 1/4 of t revival time. You can see the blue line where the initial wave packet, it has split it into two parts. And the red line, we have changed the j value. It is, it's coming closer. And the black line is showing it's kind of ripples. So it's completely changing the system dynamics when we are changing the, coupling parameter. So here actually we will see what will be the effect of rotational, degrees of freedom when we consider this. And here we studied for two particular cases. One is for the cat state, another will be for the compass state. So S is the dimension, sub-Planck dimension, where we have considered the cat state, and you can see with the variation of j values, the dimension of sub-Planck scale structure will, it will change and it will oscillate. And the initial one is the state, which is the corresponding to the state in phase space. One can check it, and the minimum value we got when it looks like that. In the right hand side, the below one, it shows the corresponding state. This is for cat-like state. Now, compass-like state, it shows this is again the variation of the smallest regions, and the initial one, its dimension, it is the sub-Planck dimension is almost 0.1 when it looks like a compass-like state. But again, the maximum sensitive structure one can find corresponding to this state, and it looks very similar to what we actually got for this diatomic molecular system when we have used the coherent control method. So this state basically shows that this is the maximum, it shows the maximum sensitivity when it is rotated, or 45-degree angle rotation is there. So it shows the maximum sensitive states. Okay, so this is kind of comparison. It is made between this cat state and compass state, and we show that when J is equal to 64, we got the maximum sensitive state. Okay, so now, so far I have discussed about this molecular system and other physical systems, where we have discussed about these Schrödinger cat states, compass state. Now it's kind of different kind of states. It's a twin Schrödinger cat state. So we know that Schrödinger cat state in optical system, we can write it as a, it's a combination of alpha and minus alpha Schrödinger cat state. It looks like this. Compass state, it's a combination of alpha, minus alpha, I alpha, or minus I alpha. It looks like this. But if we increase the number, we have some kind of generalization of these coherent states. And depending on the number, we can have different kind of quantum interference region. So now, so far we dealt with this Schrödinger cat state. One can compare with this live cat or dead cat. And we have seen that there are quantum interference region which are parallel to the line joining between them. This state can rotate also in phase. Okay, but recently there is a paper, it's from Barry Sanders group. They published in 2019. They pointed out that an array of 4 macroscopically distinguishable coherent state is recently reported as quantum tetrachromatic state, exhibiting richer phase-space structures than a Schrödinger cat state. So instead of having these 2 coherent states, there will be array of 4 coherent states, and they claim that this will be more sensitive compared to the Schrödinger cat state. So it's a kind of schematic diagram I have given here. So this, it looks like that in a line there are 4 coherent states, and in between you can see many interference structures. So it depends on many factors actually. You can distance you can manage between the 2 Schrödinger cat states. Then the interference structure will give some kind of nature. So here the claim is that the central region's interference structure will be more sharper than what we can have using when we are using the single Schrödinger cat states. Okay, so this Schrödinger cat state, it's an eigenfunction of a square operator that we know in our literature. It is quite well known. Compass state is eigenstate of A4 operator, and this is kind of pair coherent state. It's kind of a 2 mode when you describe the 2 mode of light. This eigenstate of A and B operator. So this basically well known in the literature. Now for twin Schrödinger cat state, what we actually found that we can write as a eigenstate of an operator K minus, which is in the form of A square plus B square, and that also satisfies the SU2 algebra. So we have given a 2 mode SU2 algebra, and first time we showed that this kind of state, twin Schrödinger cat state, or in a special case it can be the tetrachromatic state. That will be a special kind of case. So that will be an eigenfunction of this kind of operator, which is having a dynamical symmetry group, and so it is quite useful then to study this system. And there are certain conditions need to fulfill, and depending on that we have many situations one can study. Many parameters are there, so changing that parameter one can play around that. So here this is a geometry of twin Schrödinger cat state. Here you can see this there are two Schrodinger cat states, and D is the distance, it's the internuclear distance between these two Schrodinger cat states. Alpha is the coherent state and theta is the phase, and phi is the is the angle between these two Schrodinger cat states. So these are the parameters are there. So one can change this parameter and can have different kind of combination of these coherent states. So these 4 parameters are very important. One is the coherent state parameter alpha, phase of the coherent state parameter theta, and the magnitude of the phase space distance d, and of course the direction, that is phi. So here mainly we have considered 2 cases when phi is equal to 0 and theta is changing between 0 to pi by 2. So that basically leads to twin Schrodinger cat state of parallelogram geometry, and all of them will be confined in a plane. So first case, when we study, we can have a family of coherent states, and they all will be lying on a plane if we change the theta parameter for a given value of alpha and d. For case 2, the theta and phi, these two will be equal. And in that case, we'll have linear twin Schrodinger cat states. When this theta is equal to phi is equal to 0, that is the special case. Then the coherent state will be lying on a single line along x direction. That is what actually Berry Sanders group they have mentioned in that paper. So in our case, that is a special case, but we have many more combination of that, and we can study these 2 different kind of situation. One when these are confined in a plane, and another one which are confined on a line. Okay, so this is planar twin Schrodinger cat state. Wigner distribution we have plotted here, and here basically we are changing the theta parameters. The topmost of that figure is showing when theta is equal to 0. So it's like a tetrachromatic state, okay, and above that, this is the marginal distribution. That is the x direction marginal distribution, and right hand side is showing the marginal distribution along the p direction. Okay, now you can see that the first one is showing, it has a very oscillatory kind of structure along p direction. So sensitivity is maximum along p direction. Now, if we change the parameter theta, then rotation, you can see a rotation. And finally, the last figure, when theta is equal to pi by 2, here you can see the sensitivity, it gives maximum along the x direction. So sensitivity is changing when we are changing the theta parameter. For a particular direction, one can make use of that. If it is along x direction, one can use this state. If it is the requirement is along p direction, one can use another state. So this is for planar twin Schrodinger cat state. For linear twin Schrodinger cat state, here you see the system as a whole, it experiencing a rotation. So initially they are all lying along the x direction, and then they are rotating as a whole. And again, the rotation is quite visible here. We are changing the theta, and theta and phi both are same here. So theta is equal to 0, then pi by 8, pi by 4, then 3 pi by 8, and then for pi by 2, see they are all localized along this along the p direction when theta is equal to pi by 2. So this is for linear twin Schrodinger cat states, and the corresponding sensitivity analysis also we have done it. So here you can see this is the delta x variation with the theta parameter. The first figure is showing where the sensitivity is going, it's increasing basically, and it is having the maximum sensitivity when theta is equal to pi by 2. It is having the minimum value here, and again it will increase, and it will have a larger value when it reaches to the value of pi. So for p, it will be inverse. So for theta equal to 0, it will have the maximum sensitivity, but this when theta is equal to pi by 2, the sensitivity is less in that direction. And C is showing the uncertainty, that is the delta x delta p. So one can see also the corresponding sensitivity of smallest sub-Planck dimension from here. Okay, so this is basically, I've just mentioned that sensitivity along x direction or sensitivity along p direction, and this is the uncertainty product. Okay, and it shows that variation, basically the uncertainty of position, that red dashed line with the star symbol. It shows the variation, and it can show that how it is changing. It is having this minimum value when theta is equal to pi by 2. Uncertainty of momentum also, it was minimum, but it going up. And in the right hand side, one can see the variation of sub-Planck dimension, and we can see that with the variation of theta, it is becoming more sensitive. For pi by 2, it is having the very small value, less value. Now we make a comparison between these two cases, because we have found that when theta is equal to pi by 2, whether it is planar or linear twin Schrodinger cat state, we got that this central region, it gives maximum sensitivity, and we have done analysis, and if you see the central region, this is the enlarged version I have shown here. You see here, this is a central region where you can check that sensitivity is maximum. Sensitivity is maximum along the x direction for the first case. So maximum displacement sensitivity is obtained for linear twin Schrodinger cat state when theta is equal to pi by 2. But in the p direction, you see this is dimension is 4.4, but in x direction it is 0.1. So along x direction, its decision is maximum. For the second case, you can see that sensitivity, maximum momentum sensitivity is obtained for planar twin Schrodinger cat state with theta is equal to pi by 2. So here basically decision is very high along the momentum direction. But if we see the sub-Planck dimension, area of a single tile, then the second one, the planar twin Schrodinger cat state, it gives the smallest sub-Planck area, and this area is 0.03 order, which is which gives the maximum sensitivity. If we compare, we make a comparison between these two kind of states, then this planar twin Schrodinger cat state brings the maximum sensitive states. So this is basically the study we have done very recently, and we have submitted this paper. It's under review. So so finally, just let me conclude here. So we have introduced a kind of new family of mesoscopic superposition states that we are calling twin Schrodinger cat states. And here basically it's not random. We cannot add randomly all these foreign states. It should have some dynamical symmetry. It should follow some conditions, and these are foreign states also. And we have checked the sensitivity. The planar one will give the maximum sensitivity as a whole when we are taking the smallest tiles, the sub-Planck dimension. But it can have higher precision in other direction also. So that can be useful if we want the sensitivity or precision along any particular direction. For example, for momentum space or for coordinate space, that can be useful. So both the states will be very much useful there. So our study offers the highest sensitivity limit. So here, basically, it's much more sensitive than individual Schrodinger cat state. That is of course true, and it can enhance the sensitivity by the 1/33th of Planck's constant, the dimension what we got, that is 0.03 order. So these sensitivity parameters can be correlated to other physical quantities, like as I already mentioned, we can use this for measurement of weak forces or phase fluctuations, weak signal measurement, or any kind of application we can do for other system. Also, we can start study this same thing like molecule, waveguide array, or underground atom. So so let me just summarize the thing that I started with the molecular system. Okay, and we have shown that for the vibrating diatomic molecule, one can find the sub-Planck spin structure. These are the quantum interference structure. It has very good connection with the precision measurement. And then we use the coherent control method, which we showed that it can enhance the sensitivity limit. And then the rotational amendment part also we have analyzed. And for other physical system, for example, post-stellar kind of potential also, we have shown that, it is very, very sensitive. If system has any kind of perturbation or coupling with the environment, that will detect fast, and this smallest disturbance or smallest displacement can distinguish these two states. So then finally, we had already discussed about this twin Schrödinger cat state, which is the most sensitive one, and we got very good result and can be very useful in quantum sensing domain. So thank you very much for all of your patience.
Now we are open for questions. Are there any in the chat box?
No, there is no question.
So I'd also like to ask you. So this kind of states, for example, in optics, people have realized, but molecular physics, you might be knowing. I actually have not kept track of it. In molecular physics, I saw some works of Ivanov and others. Molecular wave packet.
Yeah, for molecular wave packet also, if we use two electronic states of a molecule and can excite two wave packets, so these two states will be coupled in that way. So in that way, we can again see the system dynamics where the two wave packets we have, and in a particular condition or situation, they can be situated on a line. So we can observe also tetrachromatic state. So that one can see. Of course, that is a very challenging task because it will give most sensitive structures. So, but of course, one can see this in the molecular system as well.
Yeah. Any other questions? Okay. So if not, let us start, Dr. Suranjana. And the participants, I just want to tell you that these are the kind of things which are going to be very important in your future, because using laser and using both matter, light interaction, and light alone, people are really coming up with amazing kind of non-classical states. So you will soon see many of their use, in the near future. And these are very easy to deal with, not very difficult to calculate. Of course, the numerical computation and drawing of those nice plots are very difficult, takes a huge amount of time. So,
yeah,
in future,
it takes a huge amount of time.
Huge amount of time. Suranjana is available if you want to send questions and things like that. We can talk more.
Yeah, if they have any inquiry, any question, they can also write to me. My email ID is there, so they can also communicate. So further, we can discuss all those points.